Welcome back everyone. So in this video, I will solely focus on teaching you how you can solve differential equations symbolically using SymPy. Now, the example we'll be considering is a very simple example of the damped mass spring system. It is kind of a generic example when it comes to differential equations, but I wanted to give you a more general purpose on what differential equations are, what their types are, basic motivation on why we want to solve these differential equations, and some 5-step process you can use to solve your own differential equations symbolic. Now, before starting, I want to briefly discuss what the damped mass spring system is. Now, if you would go on Google and just type damped mass spring system, ignore this ChatGPT window right here, but you'll see it is a mass that is attached to a spring and which is damped over time. For example, this can be, for example, a mass m attached to a spring k, which is submerged in some sort of damper that will absorb the energy. Here, let me make you a little scheme. If you have a mass m that we want to study its movements, okay, this mass m is attached with a spring here at some wall, and we can either submerge it, as we did here, in some sort of liquid that will absorb the energy of the spring and the mass, or we can represent it here by adding this component right here. This will be characterized with the damper, okay, and this will be the spring K. Now, what we are interested in is studying the movement of this mass. So x of t is equal to. This is what we are looking for. Now, it turns out that the differential equation that describes this system is m times the second derivative of x plus c first derivative of x plus kx is equal to some external force, here f ext. Now here when I say x2 dot, I refer to the second derivative in time, so x2 here, and then t squared. Actually starting to solve this differential equations. I want to highlight why do we want to solve differential equations in the first place, whether it's numerical or symbolically, aka analytically. Now you have to know that in the world and physical world and universe we're living in, some types of behavior are described by equations. And these equations are differential equations. You might not notice it at first, but for example, take the second law of Newton, a law I think most of you are familiar with. So is stating that the external forces applied on some particle is equal to its mass times its acceleration. This is a very basic, not so basic, but very general law when it comes to physics. Now, when looking at this, say, for example, here we have a particle, and you have some external forces. Let me call this F, E, X, T. This will be our particle P that has a mass m. Now, what you will notice is, from this acceleration, we know that the relationship between the acceleration and the speed and the distance is the derivative across time. For example, we know that the speed is some sort of difference in distance divided by a difference in time. If we take this difference to a very, very small difference, it will become a derivative. So we can say that the derivative of the distance, across time will be equal to the speed, depending on time. Similarly, we have the acceleration is the derivative of the speed across dt, which means that the derivative of the distance, in this case, let me call it x across dt squared, so the second derivative, is equal to the acceleration, which means here, if you replace this right here, we can get that the sum of the external forces is equal to m times the second derivative of x across dt. Now, if you replace this external force, for example, with the weight of a body, for example, here, this particle is submerged in a gravitational field of the Earth, which means that the force will be equal to m times g, which means that the mass m times g is equal to m times the second derivative of x across t. If we simplify here, we have dx over dt squared is equal to g, which can be considered as a differential equation. Now imagine if in our force here we have as well x of t, we will have here g times x of t, which is also a differential equations. Okay, so now we know that here we are interested in predicting, in a way, the position of this mass here. We can predict it by knowing the value of x depending on t, and this x is governed by this differential equation right here. One important thing when it comes to differential equations and whether you can solve them symbolically or analytically or not will often depend on the class of the differential equations itself. Now, what the class is, how do we classify them and all. To put it in simple words, to classify a differential equation, you have to look at its order. So first of all, it's the order. Second of all, it's the linearity. And third of all, it is, okay, so let's analyze all of these. Now, the order here represents the number of the highest derivative. For example, here, the highest derivative is the second derivative across time, so it will be of second order in time. Now here, the linearity refers to this x variable here. So if we have, for example, x of t squared, this is nonlinear, so NL, standing for nonlinear. If we have, for example, 1x, let's call it plus 4, this is linear. If you have square root of x of t, this is nonlinear. Here I meant L, sorry. And so on and so forth. So it is as if you can write it in the form ax of t plus b here, where a and b here can be considered as real numbers. So a and b are real numbers. Okay, so here, this one is linear, okay? And now the homogeneity is related to this second term. If it is equal to 0, it is homogeneous. If it is not equal to 0, it is non-homogeneous. In this case, it is non-homogeneous. Now, the reason why you want to know and be able to classify differential equations is for some, and in fact for most differential equations of higher order, for example, order 3, 4, and so on, and the problem that are nonlinear. For example, here, if we had, for example, x squared, or the square root of x, something like that, or we have, for example, 1 over x, or maybe the square root of x, these are all nonlinear problems, which can make the analytical solution very complicated. But in this case, this simple equation is linear, it is non-homogeneous, and it's second order in time. So we can solve it using SymPy. Now, all of this theory apart, we can finally start using SymPy to solve these differential equations. Now, it is very important to know what are the types of differential equations you can solve symbolically or not, and this you can know depending on like the classification of it. Let's go to Python. Here, the process of solving differential equations is a 5-step process. First of all, you define your equation, and then ideally you define your initial conditions, but this is not necessary at first. You solve your equation, and then you convert your analytical solution to a numerical solution. These two are optional if you want to display the results. Okay, so we will consider the simple damped mass spring system equation. Here I had some very basic overview on differential equations. So differential equations are mathematical equations that relates a function y. So we have a function y. In this case, this function is x. It is a function because it depends on t. It relates a function to its derivative. For example, here we have the function y that is related to its derivative. Here, y prime plus y is equal to x squared. This is a differential equation. This is another differential equation here. And the damped mass spring system is a second order differential equation which is linear and non-homogeneous. Whenever you have such a differential equation, it is actually a good practice to have a factor of 1 in the highest order derivative. We said that here we use the SymPy library. Now, if you don't have SymPy installed, you go to your pip installer, specifying pip install SymPy. Okay, so I already have it installed, so it will go through the process of installation. But for me, it says requirement already satisfied. Now, SymPy is a library used for symbolic computation in Python. If I go ahead and do import SymPy as SM, or SMP as you want, I like to do it as SM, okay? It allows us to create variables, to create functions, to create equations, to solve these equations and all. To create variables within SymPy, you simply state your variable, for example, here x, y is equal to sm, and then within the sm, you will call the symbols function. Symbols, okay? It takes as input a string, okay? For example, here it is x and y. Representing this one is the first variable, and y is the second variable. If I go ahead and then do x plus y, for example, you'll see that now we have a symbolic expression for x and y. I can go ahead and do it squared here and squared here. You'll see we get it did. If I want to have the sqrt, I do smp sm.sqrt, all of this. Okay, it is a symbolic way to deal with things. Now, there is a lot of SymPy tutorials out there. I'm not sure if you want to have a SymPy tutorial, but it is very straightforward, and I hope in this video you will get most of what you will need in SymPy. So looking at our equation right here, which we want to divide by m, so this would be our equation when we divide it by m, okay? Now let's create this equation. By looking at this equation, we have k, c, and m, which are constants of our problem. And then we have a function f of t representing the external force. And we have our main focus x, which is also a function of t. So first of all, we start by defining the constants. So I define the constants k, c, and m. Okay, it is equal to the sm dot symbols. Okay, sm dot symbols is whenever you want to create symbolic variables within SymPy. You first specify here a string saying that, okay, we want to represent these variables with k, c, and m. Okay. And if I go ahead and simply run this code, everything will work. If I type k, we will have this k right here and so on. If I specify here, for example, k subscript 1, now this k variable will be represented with this LaTeX formatting of k subscript 1. This is why we get here k subscript 1. Additionally, you can add some constraints on your variable saying that, okay, these are constants. I know that k, c, and m will always be positive. So we can add another argument here saying positive is equal to true. And you can say that real is equal to true. This means that these constants are both positive and real. Now this will in a way help SymPy whenever you want to solve a system or an equation to make some assumptions and to easily simplify the solution. Okay, so we have our constant. Now we want to create our variables. What are the variables of our problem? So we know that f of t, x of t are functions, and these functions depend upon t. So the variable in our case is t. So for example here, if I type in variables, my variable is t, corresponds to the time. It is an sm.symbols as well. We know that the time is positive and real, so we can add these two right here. If you want to know more about these assumptions we make, if you go here on Google and type in SymPy assumptions, it will lead you to the documentation of SymPy here where you will have all the assumptions. Wait a minute, there we go. So this one. If it is complex, extended negative. If it is negative, if it is positive, rational, real, transcendental, I don't know, zero. So you have a very wide range of assumptions. So this is the SymPy documentation, by the way, under the how-to guides and assumptions. Here, if I type in t, we have our variables. I can go ahead and type in, for example, k times t plus c minus m. This means nothing, but I can do it, which will be our equation. Okay, so now we have the constants, we have the variables, we need now our functions. Since f of t is a function of t, and x is a function of t. Now, the way to do it in SymPy, you specify here, for example, we want to define our functions. First of all, you specify the name of the function. For example, here it is x, okay? You say that, okay, x will be a function specifying sm.function, okay? You call the function class within SymPy. Here, you specify a string of what we will represent this x with. So we will represent our x function with x, okay? And if I go ahead and show you now x, you see we get this. So, okay, we know that this x is of type, let me show you. It is of type sympy.core.functions, but it is an undefined functions since we did not specify what are the variables of this function. However, if I go here x and specify of t, I run this, you'll see that now it is a function x. If I print x of t, we get this here, which means that if I specify here, I want to create a function represented by x that takes the variable t. Okay? If I print now my x function, we get this. I can, of course, go ahead and do, for example, x squared, or 4 times x squared, and so on and so forth. You see, we slowly starting to build our equation. Same goes for f. I do f is equal to sm dot function. Remember here, it is a capital F. And then I specify f because I want to represent it with f. I can either do f or, for example, here do f subscript ext, representing for the external forces of t. If I go ahead and run this and print down f, now we have the external forces depending on t. Okay, so now we have our constants, variables, and functions. We can finally start building up this equation. But you will notice something. You'll see here, we have a first derivative in time, and then we have a second derivative of time. Now, you have two choices now. You can either define it as it is. For example, here I can say that my equation is equal to. The way you want to define this equation is put everything to one side so that you have something equal to 0. We have this f of t divided by m, which we bring to the left. So we'll have, let me write this down again. We'll have here minus equal to 0. This is what we will have. So let me write this down. We know that we want to have a second derivative in time, so let me call it d dx divided by d dt, okay? And then plus here, it is c divided by m, so c divided by m times dx over dt plus k divided by m times x minus f divided by m. Now, of course, if I go ahead and run this, you'll see that we get an error saying that d dx is not defined and d dt is not defined. So to define the second derivative in times, or in general, to define a derivative within SymPy, here, let me add derivatives. Okay, so let me hide this for now. To define derivatives, for example, here, if I have dx over dt is equal to, we do an sm.diff. This represents the differentiation operator. If I want to differentiate x across t, okay, and I print dx over dt, you'll see we have the first derivative of x across t. If you want to have the second derivative of x across t, additionally, I can add another parameter here representing the order of the derivative. So this will be ddx over ddt. Okay. If I run this, you'll see that we have the second derivative of x across the second, or dt squared. Now, similarly, you can specify the integral of a function or a variable by doing a integrate here. Let me remove this. We want to integrate x across t. If I go ahead and run this, you'll see that we have the integral of x of t dt. Okay, so let's come back to diff. Okay, we want to differentiate this 2 times across t. And same goes for our dx dt. So dx dt will be our first derivative in time. Now, once we did that, we can finally build our equation. And if I run the code, you'll see that we successfully defined our symbolic equation in SymPy. Now, this is one way to do it. Another way is, instead of putting everything to one side, what you can do is use a equation class within SymPy that will take as input this right-hand side and this left-hand side. So let me actually do this. Let me comment this out saying this is the first type. So first method, for example. The second method is to define the right-hand side and the left-hand side. I can say here, right-hand side is equal to, and left-hand side is equal to. Now, the left-hand side will be equal to this part right here. So it's x2 dot plus c divided by mx dot plus k divided by mx. So it's all of this part right here. And the right-hand side will be f of t divided by m. So I do f of t divided by m. Okay, now if I go ahead and on this, you see we get no error. I want to specify the right-hand side, I get the right-hand side. If I want to specify the left-hand side, I get the left-hand side. Now, to build an equation out of these right-hand side and left-hand side, what I can do here is say my equation is equal to the sm.eq. We will be calling the eq class, short for equation, and we are going to build from our left-hand side and our right-hand side an equation. If I go ahead now and print my equation, you'll see that we get successfully our differential equation. So all of this was step one, which is here, define your equations, symbols, derivatives, integrals, constants, and so on. The second step would be to define our initial conditions, but this one we will be seeing a bit later on. I want to first show you how we can solve an equation. So this was step one, defining. Let me add a quick comment right here. Why am I specifying initial conditions and not boundary conditions? Since here we have a temporal problem. A temporal problem is a problem where our variable is depending on t. And usually the way you define conditions on a temporal problem is you look at the initial state. For example, what is the position at t is equal to 0? And what is the velocity corresponding at this time right here? So at t is equal to 0. For now, we are going to jump this step right here. I want to first show you how we can solve differential equations. Okay, so let me add another one. We are going to pass this one for now. But what I'm interested in is this one right here. Now, the way we solve differential equations in SymPy is very straightforward. If you have, for example, an equation, let me just show you this because it will be very intuitive for you later on. If I have an equation, for example, x, let's say we have a simple quadratic equation of x squared plus x plus 2, something like that, is equal to 0. Okay, so let me define this, saying that, for example, t squared minus 2 times t plus 4. Okay, so let's say this is our equation. If I type here my example, we'll see you have t squared minus 2t plus 4 is equal to 0. Now, if I want to solve this equation for t, I use solving the equation. This is a quadratic equation. I use the sm.solve. If I use the sm.solve on this equation for t, I run this. You will see that you don't get any solution. This is because here, remember, I specified that t is positive and is real. If I remove these assumptions right here, I execute this here to update, saying that t can be any variable, okay? And I rerun this part right here. You'll see that now, we get a result. We get two solutions, this one and this one. If I want to view the first solution, it is 1 minus square root of I. And the second solution, it is 1 plus square root of I. So in a way, this means that the discriminant of this equation is negative. So we get complex solutions. But since here I have made some assumptions saying that, okay, I know that my variable is positive and is real. So if I execute this, when trying to solve this equation, and let me just remove this one for now, you'll see that we get no solution since t is supposed to be real. Now let me change this, for example, here to, I think, minus 4. Let me run this. Now, you see we get solutions since our solutions are both real. I want to extract the first solution. It is 1 plus square root of 5, or minus square root of 5, and the other is 1 plus square root of 5. Now, this is how you can solve simple equations. To solve differential equations, it is somewhat the same way. Instead of specifying here the sm.solve, you specify sm.dsolve, meaning that you want to solve for differential equations. Okay, so let me remove this example here. Let's say solving our differential equation. We can extract this as our solution. So I do solution is equal to sm.dsolve. I specify my equation. So this one. Let me run this, okay. And here, the thing we want to solve for is not t, but we want to solve for this x. Since remember, what we are interested in is to know what this x here is. So this is our focus. Our focus is not in t. Our focus is in x, like so. Okay, so if I specify here that I want to solve it for x, and I run this code. Okay, so you get our solution. If I print now my solution, okay, so you'll see that our solution is very weird. Here you have C1, all of this, then the integral and all. This is another problem I forgot to specify because here we are using with a generic external forces. This is why we get in a way this weird result. If, and let's say for the sake of simplicity, instead of having here a function of f, random function of f of t, let's say I specify, for example, you want to either choose sine of t, or for example, let me set it to 0 for now. This is the most simple function. Let me run this again. Okay, so we have a homogeneous equation in this case. We don't have any external forces. If I run this again, you'll see that this is a very nice looking equation, or rather solution. You'll notice that here we have C1 and C2, which are arbitrary constants, since we didn't specify the actual initial condition of our problem. So this will be again here in this step 2. So I set this, for example, to the sm.sine of t. Let's say we have just a sinusoidal external force. If I run this again, okay, and then I run this part again, you'll see that this is our solution. It is in terms of c, k, m, like in a symbolic manner. Now, if you want to replace, for example, c, k, m with actual values, I can do here solution.subs. We are substituting k with 1, okay? And you see everywhere where we had k, it is now equal to 1. Now, similarly, if I specify here, I think it's an array, okay, of tuples, we want to first substitute k with 1, and then we want to substitute c, for example, with 0.1, and we want to substitute, let's say, m with 2, let's say. I hope this will not create any problem, but if I run this, you'll see that this will be now our solution. But we still have C1 and C2. Now, to get rid of these C1 and C2, we have to actually specify our initial conditions. So we come back here. You can say specifying our initial conditions. Now, the way you specify your initial conditions, you gotta look into this dsolve function. If I open the documentation, holding control and then clicking on the function here, if I hold control, you see it opens like a link. Okay. And then this is the dsolve function we're using and all. It takes as input ICS, which stands for the initial conditions. And then here, you'll see that ICS is a set of initial/boundary conditions for the differential equation. It should be given as the form, this one. So this is the form we should be giving it. We know that initial conditions should be something like this. It should be a dictionary. Okay, so let me write it down a bit more clear. Okay, so this is the first element, this is the second element, and then, whoop. Okay, so this is a dictionary. This is our first initial condition, and this is the second initial condition. Okay, so to understand this, let's analyze and let's set our own initial conditions. Let's say that at x, when t is equal to 0, let's say is equal to 1. Okay, and then we have dx over dt at t is equal to 0, let's say is equal to 0. Now, this part right here, so the key of this dictionary represents this. It represents where do we want to actually apply this initial condition. In our case here, in a way, in x, we are substituting t with 0. So this would mean that we are doing, for example, x.subs t and 0. Within the function x, we are replacing everywhere where we have t, we replace it with a 0. So in a way, this would represent here x.subs t and then 0. This means that we want to replace x. This means within x, we want to replace t with 0. And the value of this one here is equal to 1. Okay. And then same goes with this. We want to replace, so let me delete all of this. We want to replace in dx dt at t is equal to 0. So I do dot subs t 0. I want to have 0. So this is in a way our initial condition. But let me try and print it down. If I do here x, see, we get the x function. If I do x dot subs and then t 0, you'll see, oh, so this is subs, like so. You see that we have x of 0. And then we want to say that x of 0 is equal to 0. So we want to have this being equal to 0. So we have to have this being equal to 0, or in rather 1. So we want to have this 1, so x0 is equal to 1. This is what we just did right here. Okay. Now, by specifying here the ICS, the argument of this dsolve function as our initial conditions, okay, I run this, you'll see that we successfully got rid of the C1 and C2 constants since we applied our initial conditions. Now, I know it's long till this point, but trust me, we're almost done with it. Okay, so let's say our generic solution will be this one. Okay, so it is a very long solution since we are only dealing with symbolic expressions. You can see here. Now, what you can do is, for example, say that k-val is equal to something, and then c-value, then m-val. Okay, this you can input. For example, we have a string of, let's say here we have this example right here, which is a site called fetcolorado.edu, which is in a way you can view the simulations of a damped mass spring system. Okay, you can play with it around. But let's say we have a mass of 300 grams, okay, and a spring constant. Let's say we'll just set it out ourselves, okay. So let's say we have a spring constant of 20 Newton meter. Okay, we have a C-val of 1, standing for IS International System, and we have a M-val of 0.3, standing for 300 grams. Okay, and then I can go ahead and do solution.substitute K, and we want to substitute K with our K-val, C with our C-val, and M with our M-val. Okay, you'll see that this is now our solution. Okay, so you notice here I changed the values right here. This is because when you look at this term right here, so c squared minus 4km, I don't want this term to be a negative, so I don't want to have the complex number. So I just make sure that, so c squared minus 4km is something positive. Now, you see we have a positive solution. Once we have our solution, we have the initial conditions and all, what we are going to do is go through step 4, which is convert your analytical solution into a numerical solution. To do this, there is a function called lambdify. So here I can say that you use the sm.lambdify. Now the sm.lambdify is a function that allows you to take a symbolic expression within SymPy and to convert it into a numerical function. Now let me show you a brief example. Let's say I have an equation, for example, my EQ is, for example, t plus 1. Now I can go ahead and show you my equation. So it is basically t plus 1. And if I do now lambdifying this equation, I say that, okay, I want to lambdify this, and the arguments of these ones are t. So I specify first the arguments, and then my equation, actually. If I go ahead and run this, you see we get a function that lambdify generated. If I say this as my EQ slash numerical, okay, if I input a value of t in this my EQ numerical, let's say I say here of 0, you say we get 1. Since if we replace t with 0, my equation becomes 1. If I replace t, for example, with 2 times 2, which is 4, it is 4 plus 1, which is 5, and so on and so forth. Now, similarly, what you are going to do is say our solution underscore numerical, it will be equal to the sm.lambdify, so lambdify. We specify the arguments here, In this case, the only thing that it is depending with is this t variable. So I specify here t, and you want to convert this solution. If I go ahead and run this, you'll see that we get our numerical solution. Now, if I use a NumPy array, for example, I do import NumPy as NP, and I create a array of times. For example, it goes from 0 to 10 across 101 points, and I do solution of, let me call it t numerical, here t numerical. I go ahead and run this. Now you'll notice that we get an error here saying that name x is not defined. This is because I actually made a mistake here. Whenever we want to lambdify the solution here, when we pass in this solution, we tell SymPy that, okay, we want to lambdify all of this equation, including this part. But in reality, what we are interested in is only this part right here. So if I specify here solution, right, we get this, all of this weird thing. If I specify solution.RHS, only the right-hand side, you'll see that we get only the right-hand side. So similarly, if here, instead of giving it the whole solution, so all of this, I want to just give it this part right here. So if I do here solution dot right hand side, the solution dot right hand side here, and I want to actually solve this as my new solution. Okay, so let me rerun now this one. If I go ahead and print the solution, we get this one. If I do solution dot RHS, we just get the right hand side. If I do LHS, we get the left hand side, but we are interested in the right hand side. Okay, now if I specify here the solution dot right hand side and I rerun this, you'll see we get actually a numerical solution since we inputted a numerical value of t, and we have successfully generated a NumPy array of our solutions. Now I can go ahead and save this as solution numerical. Now the fifth and last step, I know this has been a long video, but we are finally reaching the end, is to display our results. If we import the matplotlib module, so import matplotlib.pyplot as plt. By the way, if you don't have matplotlib.pyplot and NumPy installed, here, NumPy, all you gotta do is a pip install NumPy, okay, and then you do pip. So let me actually move this a little bit up. Pip install NumPy and pip install matplotlib. So you'll see that I have them both installed since we've been using them quite often in this channel. Okay, so once I have matplotlib, I can simply say plt.plot t numerical with our solution, which is numerical. If I go ahead and run this, you'll see that we get this solution right here. Now, if I want to increase the number of time steps, let's say we want to study this problem from 0 to 100 seconds, I will run this, I run this part, and you can see we get this. And let's actually have no external force. Let's say we don't have any external forces. Okay, so let me run this code again, and then this part, then this one as well. You'll see that this is the solution we get. If we substitute the values, we get this one. Maybe decrease a little bit the value of k, okay? And let's say that we have, for example, there we go, we have 2 exponentiation of minus t and so on and so forth. If I go ahead and run this code, and then run now the plot, you'll see that the damping is so critical that we instantly go to 0. Now you can go ahead and play around with the parameters yourself. For example, if I set here k is equal to 10 newtons meter and m is equal to 1 kilogram. Okay, and then I set c to some value here. I run the code, you will see that we get a slowly oscillating and decaying signal. It will be in a way corresponding to, for example, as if I do this case right here. So I run the simulation, but if I increase a damping, you'll see that it will slowly lose its energy and then come back to its initial position here, which is 0, which is the same thing in this case. I can also add a grid. So grid. I do a plt.grid, and this would be our solution. So feel free to play around with these parameters right here, the k, c, and m. Okay, if you want to go, you can ask ChatGPT what would be the right values for right terms. For example, here, if m is equal to 1, k is equal to 10, we can take c is equal to 1.26 Newton seconds per meter, and so on. So you're free to change the parameters as you want. Now, I'll try to make this code a little bit more visually pleasing, and I will upload it. If you followed along, thank you so much for sticking around until this point. It was a very long video, I admit, but I hope you were able to understand, since understanding is the most important thing when it comes to learning something. I hope everything was clear. If something was not clear, let me know in the comments. I'll try my best to answer it and hopefully clear out any confusions. So I hope you enjoyed watching this video. If you did, consider subscribing and liking the video, which will help me to do more of these videos. And that being said, I hope you study well, and I see you in the next one. This has been Yunus, and peace.